trick of algebra. The richest definition of delta t is the difference between the two times. So it is t2 minus t1, which is exactly what we have in the denominator here. And delta y will be y at t2. This is the better way to write it. Delta y will be y at t2 minus y at t1. Okay? Now, from here, I can view it as delta t is a difference between the two times. Or I can add t1 to both sides and get t2 is t1 plus delta t. The second time here is the first time added a time period, a time interval. Yeah. So I can view it as I'm looking at the y position at some later time. It is delta t later than t1. I am just replacing t2 here with t1 plus delta t. Okay? And then this is still t1, and then divided by delta t. If you look at that formula, it seems like t2 disappears. And what I'm going to claim is that you can actually make t2 disappear and make it not important. The way to do that is to just take delta t to be smaller and smaller and smaller. As long as delta t is small enough, t2 doesn't matter, or the value of delta t doesn't matter. I show it by taking delta t to be 1, and then half of that, and half of that. And after I calculate the y velocity, you see the y velocity change by twice, by 1. And if I keep going down by half for delta t, the y velocity I get 2 point something, 1.2. At the end, the ratio will be approaching 1, which means that the y velocity stops changing, even though the delta t I'm using is shorter and shorter. So as long as the delta t you use is short enough, what you choose to be delta t doesn't matter, and you will just get a well-defined value for your by. It's going to be something like 5, and then after you multiply by 5, it's still by 1 is still 5. So the delta t is keep getting smaller, but the by you get is always the same at the end. Okay? So in order to denote a small delta t, I'm going to use this small delta, which means that I'm taking delta t to be very small, about 0. Now you see this delta, right? Good. No, it's not good fun. Anyway, that small delta just means it's very small, and about 0, yeah. In this case, I can just write this y velocity as a function of just t, because if I don't care about the value of delta t, then I don't need to distinguish t1 and t2. I should just call it t. So the y velocity will be the y position at some later time minus the original y position divided by that small change of time. It is the rate of how y position changes, and you need to take the interval to be very small in order to have a well-defined function. So not only y and x position is a function of time, the x and y velocity are also a function of time, as long as you take delta t to be very small. Okay? So then what will you get if you take the RT to be very small? What you get is the slope of this tangent line. So here I choose t to be 0.5, and what I get from computing this y velocity will be the slope of this tangent line, which just passes through the curve at t equals 0.5. So y velocity can be visualized as the slope of tangent line at that time. It is a function of time because if you go to our time and compute the slope of the tangent line, you can see that the slope of the tangent line should change, as you can see the different red line is having different slope. So what I did is I just choose delta t to be something like 0.01 second, and I figure out the y position at some later time and subtract it with the original time divided by 0.01 second. You can do the same thing for your homework, and you should get some different value at different t. In the beginning, you can see the slope is positive, so I get a positive value. And as I go to later time, the line goes down, the slope becomes negative. And indeed, I get negative value for By. So if I plot By with the time I'm using, oops, you see it goes from positive to negative. So this is how the y velocity looks like if the y position looks like this. Any question? Have you guys learned this before? Okay, alright, good. Anyway, it's good. So this is for the y position. So for a yt graph, the graph is a curve, the y velocity will change. For this ball, I look at this ball. This is the ball in the tree frame. Let us review what it looks like. We are looking at the ball in the tree frame. The y position goes up and down, while the x position just keeps going to the right. And if you plot xt graph, it's just going to keep increase with time. And no matter which point you choose to compute your Vx, the slope is the same. Vx now is also a function of time using this small delta t. So if you look at the Vxt graph for this ball, it's going to be a constant value too for all time. And if you try to plot the tangent lines like the yt graph, all the tangent line will just overlap with this xt graph because it's just a straight line, and the tangent line of the straight line is the straight line. Okay. So let me summarize some feature or some common mistake when you are plotting the SD graph and YT graph. And we have already know what x velocity and y velocity is. These are the definition. So are you guys comfortable with this notation now and function later? Okay, good. So because the x velocity is the slope of the tangent line, let me draw the xt graph. The first common feature is that when the x position reaches some maximum, at that maximum, the tangent line should be flat with zero slope. So when your position reaches a maximum, your x velocity should be 0. Okay? So if you plot the x with t at this same time, your x velocity should be exactly 0 when you have a horizontal tangent line with 0 slope. Okay? Same thing with a minimum. At the minimum, the tangent line is also flat. So the x velocity should also be 0 down here. Okay? Now, let's say the entire graph looks something like this. What I know is that at this part, the x position is increasing. To increase x position, you need a positive Vx. Right? And at this part, the x position is decreasing. To do that, you need a negative Vx. So the Vx here should be somewhere down here in the negative part. When I go to here, the x position is increasing again. So I know the x velocity should again be positive. So the x velocity corresponding to this xt graph should look something like this. It should pass through 0 whenever the x has a 0 slope, and positive when the x is increasing, negative when it is decreasing. Okay? Now, let's see a common mistake. When I have a Vxt graph that is going up like this in the negative part, will the xt graph also go up? Yes? No? Let's try this again. If the Vxt graph is negative and is going up, will the xt graph go up? Yes. No. Good. Because if the y velocity is negative, it means that the x position should be going down. So what might correspond to this Vxt graph? What corresponds to this Vxt graph should be a xt graph that is decreasing its x position. And it will decrease like this because the x velocity is approaching 0, which means that the slope should approach a flat 0, so the curve is curving upward. Okay? Now, when the Vt graph is still negative, but it is going down, it becomes more and more negative. The velocity should go away from 0, which means that the slope should go away from 0. So you should become more and more steep in the xt graph. Any question? Okay. So now we can look at the unicorn. Remember the unicorn? The unicorn is doing here, jumping left and right. So if you look at the unicorn in the tree string, you can see that the x position should decrease and increase. So that's why the xt graph looks like this. It decrease and increase. The corresponding Vxt graph should have all these features. Oops. At this time, which at this time, the x velocity is indeed 0. And when the x position is decreasing, it should be negative. When it is increasing, it should be positive.